small dilatation pseudo-Anosov mapping class.
First, I'd like to thank the organizers. This has been really fun, and I think this was conference. Okay, since I have a lot of pictures, I decided to make slides at the last minute, so complete. So let me just start out on the board, and I'll do the slides. So the idea, the question is, what do small dilatation pseudo-Anosov mapping classes look like? So let me just remind you, just in case, very, very quickly, what a pseudo-Anosov map is and what. Maybe I don't need to do that, but okay.
It's nice.
Yeah. So first, so let S be a compact oriented surface, finite height. So it could have boundary, and so phi is going to be in the mapping class group, which is just homomorphisms of S narco isotopy, well boundary, I guess it has boundary, or it could actually also, sometimes we think of surfaces with functions, finite. And then by the Nielsen-Thurston classification, there are three types. There's the periodic. So I picture, I mean, there are different kinds, but here's a kind where you have this periodic rotation. Reducible, which means that there's some curve on the surface such that the mapping class raises some power, reads it fixed, reads it invariant, or a bunch of curves. And the other possibility is pseudo-Anosov. And in the pseudo-Anosov case, there's a way to sort of put a foliation, a pair of foliations, transverse foliations on the surface outside of singular points, or the singular points is going to, the foliation might break down like this. But these are just isolated, finite number of isolated points. And near the boundary it could look like that, similarly, etc. And then there is a lambda called the dilatation, and it's a number bigger than 1, so that these foliations, so first these foliations are phi invariant, and phi stretches, they have transverse measures, and phi stretches in one direction by lambda, and in the other direction by 1 over lambda. So this lambda is called the dilatation of the mapping class. And so we're interested in knowing things about the dilatation. So this dilatation is, it's always an algebraic integer. And I'll talk about that more. It's a special kind of algebraic integer. Henner showed that if you let delta G be the minimum lambda for a fixed G on a closed, so this is, the S is the genus G and the closed, right? Then this is log of this is S in charge 1 over G. So in particular, as you let G get large, delta G will get small, and it goes small like this. So this kind of started people thinking about, so what is the value of lambda G? And also what happens as you go to, there's some kind of constant, these constants, bounding delta G to the G. So what can we say about these constants? Maybe this has an actual limit. Or at least what are the accumulation points of this thing? And then finally is what do mapping classes, pseudo-Anosov mapping classes with small dilatation So let's say small just means that lambda to the G, or let's more generally, if you have functions and things like that, let's say asymptotic Euler characteristic. This is called the normalized dilatation. When this is bounded, you can say, okay, so this has small dilatation. What do these things look like? I mean, is there a way to construct them kind of systematically? Okay, so that's what my talk is going to be about. I'm going to try. So this is not very much is known. Delta G is only known for G equals 2. So that's it. And so not even knowing what to shoot for, we don't really know what the small dilatation mapping class is.
What happens when G equals 1 that you have them also?
When G equals 1, yeah, you could have, I mean, we usually look at the hyperbolic, but we could take like G equals 1 and you know, the puncture or boundary component. Then it's just the 2, 1, 1, 1 half.
All right.
Yeah. So they're always going to be elements of FLT. So you just look at the trace, you can minimize the trace while still being hyperbolic. So that'll be the T. Yeah, so G equals 1 is known. G equals 2 was much harder and was proved in 2005 or something like that. Okay. Okay, so I said that one question is what happens when you look at sequences of these things? What's the smallest accumulation point? So first, yeah, I defined normalized dilatation. So there's a kind of conjecture or question. Is the smallest accumulation point for normalized dilatation 3 plus square root of 5 over 2 quantity, squared, not square root of 5 squared. Is it equal to gamma to the 4th, where gamma is the golden mean? And so there are 3 pieces of evidence for this. So I'll start with that. One is a question posed by Leno and Tifo. What they did was they did a lot of computer searches based on some properties that the polynomials defining the dilatation should have, and they so they came up with sort of lower bounds for low degree of what the dilatation, or at least even what the polynomials look like, even more than just dilatations, but the polynomials.
Wait, I'm confused about why the squared's there. There's 3 plus root 5 over 2 is the genus 1, instead of 1.
And then you square it because the Euler characteristic of the 3-punctured disk is 2. So right. Here I'm taking G. Now from now I'm going to take Euler characteristic. And
So is that conjecture about all surfaces, or did you? This is for all.
this is for all surfaces.
Okay.
All surfaces, including punctured disk.
So the
It's
accumulation, like
accumulation points. So
for each surface, you look at the accumulation points for that surface.
no. Sorry. Okay. So for when you're looking at
Yeah, but also not so all surfaces.
all surfaces, pseudo-Anosov and all surfaces.
Okay.
Yeah. For this story, it's better to not fix the surface because, as you've seen, I'm writing on the fact that a lot of people have talked about fiber faces. So we know that if you have a pseudo-Anosov mapping class, defined on a surface, so I'll just think of this as a pair, then that gives you a three-manifold. If it's pseudo-Anosov, this is has a hyperbolic structure. And so you have this Thurston norm wall, which looks nice, and there's a fibered face that this thing lives in as a rational point inside some kind of fibered face. And so you can think of these other points as sort of neighbors of this point. But because, I mean, if you go into what it means to have the same fibered face, if you take a neighbor of that point, it means that the dynamics of it are somehow very much related. So, and in particular, for example, as Spencer and Chris talked about, the normalized dilatation, if you think of that as a function of the projection onto the fibered face, is a convex function that goes infinity toward the boundary. It's a nice function. And so if you bury inside a thin cone, then the dilatation normalized is not changing very much. So it's so if you want to think of sort of deformations of a mapping class, you don't want to fix the genus at all. And so here, really now I'm just thinking of the set of all dilatations for all pseudo-Anosov mapping classes. But there's a surface involved in there. And so I just take look at all these things, and then I want to know what's the smallest accumulation point outside. Okay, and that's, so inside there's a, there is a case when you get gamma to the fourth on the dot, but that's also the conjectural smallest accumulation point. There are other smaller normalized dilatations, but the conjecture is that they're just sporadic. Okay, so Lenoir and Tifo had a lot of sort of computer evidence, and so let me go. So I'll talk about their question in a little while. Another one is this famous example of the simplest hyperbolic braid, monodromy, and that which has that normalized dilatation. And then a very recent result of McMullen about properties of Perron-means. And so all these things very much point to the idea that gamma to the fourth should be the smallest accumulation. Okay, so Lenoir and Tifo's question is about orientable pseudo-Anosov maps. So we restrict to the orientable case. And for those, a few more are known. So if we just look at general pseudo-Anosov mapping classes, the minimum is known for G equals 2. For orientable case, orientable means that the fibers, the foliations are orientable. The stable and unstable foliations are orientable. Of course, the surface is always orientable. But if the foliations are also orientable, then for G equals 2, 3, 4, 5, skip 6, and then 7 and 8, the smallest dilatations were found. And their polynomials kind of look different. I think I'm going to show you the polynomials later. I'm going to put them on the slide. They kind of look different, but they're actually, there's a hidden relation amongst them. That they are all factors of a polynomial that roughly looks like that polynomial there. The x to the 2g minus x to the g plus 1 minus x to the g minus x to the g minus 1 plus 1. Yeah?
Is it easy to say why 6 is harder than 5 or 7 or 8?
No,
Okay.
that's a mystery. That's a really interesting mystery. I mean, one way to say it is just that, the things that we looked at, 6 is a problem. But yeah. There's very interesting things about 6. For example, the smallest dilatation for orientable genus 6 case, the smallest one I mean, a lower bound is that Lenoir-Truffaut bound, that's equal to the small dilatation for genus 5. So suddenly, although usually when you go, because delta G is going to go down to 1, you expect that dilatation gets smaller and smaller. But we know, even though we don't know what delta 6 is, or delta 6 plus is, we know that it's at least delta 5. So the dilatations are not strictly decreasing. So it's not going to be, you know, there are going to be irregularities in the way that delta G goes. So Lenoir and Truffaut noticed that for G even, the numbers, of course we don't have a lot of data, but for 2 and 4, even just from that, they thought, well, for all genus even, is it true that the minimum dilatation is given by that polynomial? And then
They have examples realizing that?
and they had examples realizing 2, 3, 4, 5.
No,
They had
that
lower bound.
polynomial, is that polynomial realized in every genus?
Yes. But that was, yeah, that's the next result. So, and then the limit of the normalized dilatations is, if you take the Euler characteristic, is gamma to the 4th for such a sequence.
What's the power in the second term in the polynomial?
G plus 1.
G plus 1.
Yeah.
I thought there were 2 G minus 1s. I was like, well,
Oh, right. But if you replace the 1 by other numbers, then you get the other, so for even ones, you always so far get this. But for the other ones, you have to replace 1 by maybe another number that's smaller than G. But that form of polynomial seems to be really important. Okay, oh, I didn't write it down. Oh, I think later on I write it down. But anyway, so yes, all of the, as we'll see, all of the even genus oriented ones are realized. So the other piece of evidence I talked to you about is Perron units. So a Perron unit is a algebraic integer, which is the special radius of some Perron-Frobenius matrix that preserves a symplectic form. So, and those kinds of matrices come up when you're studying pseudo-Anosov mapping classes. In order to compute the dilatation of a pseudo-Anosov mapping class, one way is to take a train track map, and as we've heard, and so the transition matrices are those things that kind of Frobenius matrices that preserve symplectic form. Not quite. It preserves symplectic form on a weight space of it, and so just in terms of linear algebra, you end up getting a Perron-Frobenius matrix, and so the dilatation is the spectral radius of that thing. So that's always a Perron unit, and every Perron unit can be obtained that way, in terms of that kind of matrix. So McMullen showed that the smallest Perron unit, normalized by the Perron-Frobenius degree, so the dimension of that matrix is gamma to the 4th. So that's a very strong piece of evidence for that conjecture. Now that doesn't solve the conjecture, because when we normalize for mapping classes, we are normalizing with respect to the Euler characteristic and not the Perron-Frobenius degree. And that gap could be reasonably big, like factor of 3 or so. So it doesn't solve the problem. It sort of means that you might have to go to a higher degree or to get the dilatation. That would make the dilatation possibly smaller. And the idea of the proof is that, I'm saying this because diagraphs are going to come into what I talk about later. So every Perron unit comes from a Perron-Frobenius matrix. From the Perron-Frobenius matrix, you can make a directed graph that has these nice graph theoretic properties, strongly connected, aperiodic. And then a directed graph, in turn, has what's called this cycle complex or curve complex, which consists of the complex, simplicial complex generated by vertices corresponding to simple cycles on the graph. And so from that information, you can compute the characteristic polynomial of the Perron matrix in terms of this cycle graph. And I'll give an example in a little while. So what McMullen did was he classified, it's hard to classify dot graphs, but what he did was he classified the cycle complexes. And that caused a huge simplification, so that in the end he says it comes down to about 12 graphs that you have to check, and then you just check it by hand, and then you get this result. But this is a very strong, since it's only about graphs, it seems to be highly applicable.
Is there anything known about mapping classes that are normalized by degree, algebraic degree?
No, the algebraic degree, that's even more mysterious. I mean, he was normalizing with respect to the Perron-Frobenius degree, and that's not the algebraic degree.
Oh.
Yeah. Are there any other questions? Okay, so I gave you the first two reasons, and now I'm going to concentrate on the third reason. Basically, I'm just going to say, okay, so how do you get, gamma 4 is actually realized. It's realized by this, the mapping class associated to the simplest hyperbolic braid. So this braid, if you think of it as, if you take a disk with 3 points and you push it down and you let the points move around, we get the disk back and 3 points back. That mapping class is called the simplest hyperbolic braid monodromy, and its normalized dilatation is counted before. So let's do this thing that people have been talking about taking the mapping torus of it and looking at the fiber cone. So we know that this somehow sits inside a fiber cone. Now if you look at this, it's not hard to see that the mapping torus will actually just be the complement in S3 of that link. You just take the braid and you encircle it. So it has it's a 2-component link, so the first Betty number is 2, and as we heard from last talk, that's a good thing, because if the first Betty number is bigger than 1, then we know that if there's one fibration, there's an infinite number of fibrations. So in fact, there's a sort of a one-dimensional, the rational points on this, some one-dimensional Y segment is going to, all those points correspond to different mapping classes on surfaces of various complexity. And actually you can think of, since we're normalizing with respect more or less to the Euler characteristic, and Thurston norm can be thought of for the fibered points as the Euler characteristic of the fiber. So these rational points, the denominators, are the Euler characteristic of the fiber. So if you want to picture what's the complexity of the surface as you're moving around, the further away you go, so the bigger the denominator, the more complex the surface. Okay, and then that's another picture of the link, and it's you can see that it's a symmetric link, so you could interchange the roles of each of the components, and that gives you a very symmetric picture. Okay, so here's the fiber cone, and yeah, here's the, so for, if you look at the 2, 4, skip 6, 8, 10, skip 11, then you get and you can check it's orientable because you can also compute the Alexander polynomial. So it gives you a sequence of orientable pseudo-Anosov mapping classes for G even. And I'm not going to go into the Teichmuller polynomial, but the Teichmuller, you can just compute the Teichmuller polynomial one time, and that'll give you all the characteristic polynomials. And so you see that the characteristic polynomial is going to be that LT polynomial 1G.
So I'm sorry, I just lost the train. So all these pseudo-Anosov maps are actually monodromies of vibrations on a fixed string manifold. Is that correct?
Yes.
Coming from that cone picture.
Right, that
And-
fixed three manifold is just a complement of that braid, that encircled braid.
Okay,
So
so
we take this three manifold M.
okay, so that's the three. So originally, it as you built it, its fibers is punctured disc,
Yes.
and then you're finding the other. So why are they? How's it closed in the end?
Yeah, it's, okay, it's not closed,
Right.
but, so there's a little bit of work here. You have to show, you know that the Euler characteristic is going up. Those horizontal lines are level sets of the Euler characteristic.
Yeah.
But then you need to know, is the genus actually going up? What is the genus?
Yeah, I see.
So you can compute it's easier to compute the number of boundary components.
Yeah.
So you compute that, and so you figure out what the genus is from the Euler characteristic.
But
And so you can tell that the Euler genus goes up. But for when 3 divides the height,
Yeah.
the number of boundary components suddenly goes from 2 to 4.
Okay.
I think the confusion is sometimes you have a pseudo-Anosov on a surface of boundary, sometimes you can just cap the boundary.
I see
Yes,
that, and
yes.
then you cap it off.
Right, yeah. So you know what the genus is, then you cap the boundary. You can cap the boundary as long as the type of singularity it's not a pole singularity. So checking all that, you could actually find a closed sequence. And yeah, when you close it, the dilatation doesn't change. The invariant foliations don't change as long as the singularity is complicated enough. Okay, so from this example you get, so the open circles are orientable examples, and they give you the smallest known, so the minima for the genus, small genus that are known. So all of those occur here, except for G equals 7. And then the black ones are actually smaller dilatations or non-orientable. So, but we don't know if they're really minimal, but they're anyway small. Okay, so the second part of the question, I mean, I don't know whether gamma to the fourth really is the smallest, but here we have lots of sequences. I mean, we have sort of a deformation of something whose normalized dilatation is gamma to the fourth. So everything else has normalized dilatation close to being gamma to the fourth. So let's take, if you take this sequence, so 1, 1 is on the boundary, so it's not fibered, but 1, 2, 1, 3, 1, 4, 1, 5, those correspond to points on the fibered face, which converge to the thing that gave you gamma to the fourth. So the normalized dilatations are close to being gamma to the fourth, but the genus is going up. So I'm going to for the rest of the talk, give you 3 different ways of constructing those examples in a very constructive, explicit way. So just now we're going to forget about the fibered face. So this is the thing about fibered faces is you can say, okay, these things exist, and you can compute a variance of them, but it doesn't tell you how to actually, build it with your hands. So that's going to be the goal for the rest of the talk. Okay, so the first way is think about Coxeter mapping classes. So a Coxeter mapping class is really just simply take a graph, and for every vertex on the graph, make an annulus. And for every edge, glue the annuli together. So that's pretty much all it is. Okay, but I'm going to do, so Coxeter graphs, I'm going to do sort of slightly a generalization of Coxeter graphs in that I color the vertices black or white, or empty or full. And that's going to correspond to taking the annulus and associating it either a right Dane twist or a left Dane twist. And so for each annulus now I have a Dane twist, and I also order the graph. So I'm putting much more structure on the graph. But I've ordered the graph, which really just if you just put arrows in the direction of larger, then that's enough information.
Oh, the vertices.
I order the vertices, yes. I order the vertices. Okay, and now I have a surface, which is not uniquely defined because there was the, like with those three, I could have put them in a slightly different order. But anyway, I get a surface associated to the graph, and then with sort of these core curves that correspond to vertices, and then for you choose, say for the black ones, I do a positive Jane twist or right Jane twist, and for the white ones, I do the other left Jane twist. And so that gives you, and you do it in the order based on the ordering of the vertices. So that gives you a surface and a mapping class. And the reason why this is kind of nice is, one reason this is nice is because Coxeter systems have these nice, so a Coxeter system is just a reflection group with reflections associated to each vertex on Rn, where n is the total number of vertices, and it has a really nice presentation, very similar to the Arden presentation, but you stir all the generators. And the behavior of the product of the generators, which is called the Coxeter element, tells you is highly related to the type of the Coxeter group. So there's this nice theory that you can use to understand the Coxeter element. And the Coxeter element is a matrix, right? It's a product of reflections, and that turns out to be equal to the action on homology of the mapping class I just described. And so with generators, that's why I oriented those loops, but with generators properly controlled. So there are reasons why it's kind of nice to have a mapping class that's associated to a Coxeter graph. These kinds of examples were studied by Thurston and also by Chris Leininger. So they've been seen before. Okay, and so if you look at the known examples, Lenoir and Tifo examples for genus 2, 3, 4, and 5, it turns out that they're all Coxeter mapping classes. So you can, when you have things that, so really this side, they're all Coxeter mapping classes as I've described them, but there are ways to simplify, but we can ignore that for this. So yeah, so here are the graphs, and you see, so actually these ones, this is the hyperbolic extension of E6, E7, and this is the hyperbolic extension of E8, so that some of them are well-known graphs. Now this one, for 3, you might expect to have the hyperbolic extension of E6. And in fact, the dilatation is the dilatation of E6, a hyperbolic extension of E6. But you can't realize that for genus 3. You can only realize it for genus 4 with 2 punctures.
E6 here means equal dilatation.
Yes, equal dilatation. Yeah, so I think that somehow reflects some of this sort of irregularity in the pattern, I think reflects an underlying thing that you really need to look at when you're looking at dilatation. Okay. All right, so now I want to construct small dilatation mapping classes. And so the idea, the philosophy is start with something that's periodic. Like AN graph is a spherical graph. You want to start with something periodic and then do something small to it that makes it not periodic, makes it hyperbolic. And then, if that's small, the dilatation should be small. Now for Coxeter, for classical Coxeter systems, the dilatation is actually monotone. So McMullen proved that the smallest dilatation occurs for the E10 graph. And of course, if you make the graphs complicated, you know, it's not any good. The dilatations are going to go up. So what's interesting about these mixed sign Coxeter systems is you get plenty of periodic, you know, really complicated looking periodic mapping classes, or periodic Coxeter elements. And so if you take those and you do something to it, then you might get something small.
Is
So
this
for-
the full list also? Or is that like,
No, they're not classified or anything, but, yeah, I don't know any classified, but if you just kind of look around, you can find these other periodic mapping classes
I
that,
meant on this first table.
Oh, sorry, this?
Is that a complete list? Are there any other Coxeter graphs that you just do?
yeah, you can, but these would give you the minimum one. I
Right,
should have
right.
said that, yeah.
Are these the only minimal ones? That's my question.
Oh, can you get are there other graphs that give you the same dilatation?
Yeah.
So notice that some, like, these black ones are classical Coxeter systems. And I would say no, you can't. And now it may be possible because these other ones are bugging. You might be able to get them. Okay, so this turns out to be periodic, this thing here. And I put an ordering on it so I can make a mapping class out of it. And when you make the mapping class, you get this surface, which may be a little bit hard to see, but it's drawn like this because if you look at the boundary, you might be able to see that it's actually just the full twist braid enclosed. So that's the Coxeter mapping class for that graph is actually the monodromy for the full twist braid where you take a certain cipher surface, and it's periodic. Okay, so that gives you a lot of examples of periodic mapping class. Just do full twist braids and do the corresponding thing, and the graphs tend to look like that. And then you can take those, and of course, if you have a full twist braid, you can also do another full twist, another full twist. That corresponds to taking these graphs and just adding them together like this. Okay, so let's do the one case. You just have one vertex, and then you add another vertex, another vertex.
So, I'm just confused how you're adding on vertical. I mean, before when you added along, like, by one vertex at a time, but here you're building a bunch of vertices.
Yeah.
So,
Yeah, I'll explain. So it's actually a Murasugi sum when you do that. I'm going to talk about Murasugi sum later. But yeah, it's a nice process where you're sort of just making this nice kind of connect. But this example is very well known. So you take the AN graph, and the AN graph corresponds to just two strands. And if you take those generators, which I drew, these are disjoint from each other, and these are disjoint from each other. You take the union of those things. You can redraw this like this. Basically, this octagon is, well, I don't know if this would be an octagon, but you think of this whole thing as kind of being an octagon. And you can think of this surface as being two polygons glued together by strips that twist. So now contract the boundary, and what you'll get is the surface will look like this, where, like this, so parallel sides glue together, kind of opposite. Or another way to say it is you number this clockwise and that clockwise, starting with one here, and then you glue together the same number. Okay, so that side glues to that, etc. So that gives you a surface, and the monodromy is not hard to see. It's just you rotate, and maybe you exchange, but it's basically a rotation. So it's very clearly periodic. So what if you do that with the other one? So if you take the 2 by 2 one, that corresponds to taking triangles. And the trick is you just take your polygon and you start labeling them like A, B, C, you always go same direction. I went the other way, so counterclockwise. And then you have A prime, B prime, C prime, A double prime, B double prime, C double prime. And then you have the blue squares, which are A prime, A double prime, etc. And then you glue accordingly. That actually turns out to be the cipher surface with contracted boundary for the 3-strand braid. And then you can glue those together. So, the monodromy, again, all those triangles you just turn in the same direction, and everything will fit together. And so you get an automorphism surface period. Or if you, I think actually, at the same time, you also rotate the picture. So it's a periodic map. So here's a case for genus, for squares. And this is kind of nice because they have this flat structure. So from that point of view, it has actually lots of homomorphisms attached to it. Lots of linear maps attached to it.
Those are all positive twists.
Yes. Sorry, all negative twists, but yeah. And like, for example, that's the beach surface right there. So these are kind of like, these also have a lot of linear.
Is there an easy way to go from the graph to the picture without drawing the bands and collapsing?
I can tell you other ways of visualizing it. But. Okay, so let's take the thing corresponding to 3-strand twists. And in terms of that three-manifold we talked about originally, you're taking the braid and you're doing a full twist. That's just doing a day surgery on the encircling link, so you're not changing the homeomorphism type of the 3-manifold. So of course it's going to stay in the 3-manifold. But it turns out it actually is, and it's still going to be fibered. So it actually turns out to be a sequence of mapping classes on the fiber phase, and it's a subsequence of the sequence I was talking about. So these graphs, so subsequences of this line of mapping classes can be described using these graphs. And you can kind of convince yourself by looking at the picture. So for example, when G equals 5, that turns out to be the 1,6 example. That's this famous minus 237 pretzel that gives you Lamar's number. And it's the smallest genus 5 or n equals to an alpha number. And you can get that, so this is one explanation of why you can get that by just taking the simplest hyperbolic braid and doing I think a 2-ding twist, two full twists. So this is, I think what Kurt McFarlane likes to say is, that the golden mean and Lamar's number are in the same family. Okay, so here's another. So here's the second way. And this is so start with the pseudo-Anosov braid monodromy. So there's a train track for it. If you don't know what a train track, I think I don't have enough time to explain, but it's sort of like visually, intuitively, you can sort of see it's just some kind of graph that's sort of has this sort of smooth structure on it. And what you should think of is that when you follow along the train track without going straight over a cusp, that's giving you kind of curves on the surface. And what happens is, since it's a pseudo-Anosov map and this is a compatible train track, if you start with any simple closed curve on the surface, then eventually it becomes a curve which goes nicely over that train track. So the dynamics of the surface homomorphism just depends on how it acts on this train track. And you can see, as you iterate, that the train track shape more or less stays the same. And the transition matrix is given by this matrix. And the dilatation will be the largest root of the largest eigenvalue. So this is the spectrum. This is the characteristic polynomial, and so the dilatation is gamma squared, and normalized will get gamma to 4. Now I wanted to start emphasizing the digraph because I want to link it with McMullen's result on digraphs. So here is the associated digraph to this train track map. So the pink edge. You only really care about those longer edges. The shorter edges are always going to stay short, so they don't really matter. So the longer pink edge and the longer blue edge, if you follow what they do, the longer pink edge goes over the original longer pink edge and the blue edge, so one each. So think of this as that pink edge, it goes to itself and a copy of the blue one. The blue one goes over the pink one, and then twice over the blue one. So it goes, there's an edge this way, directed edge this way, and 2 directed edges to itself. So that's the associated digraph for this map. So now how do we find the train tracks for these neighboring points, the deformation? Well, what you do, I think Spencer talked about this, is you take the surface, look at the invariant homology, and that determines a covering, as infinite, in this case cyclic covering, or z to the first rating number -1 covering. So you take that covering of the surface. So this is really the punctured disk. So this was the original fibration. It was the fiber was a punctured disk. So to get this relative first homology class will give you the dual is an element of the invariant cohomology. And so to get the covering, all you have to do is cut along these slits and then glue them to each other in this way. So that's a picture of the cover, corresponding cover. And now you can, in here in blue is the train track lifted up. So, and then the train track map still also lifts, and you can compute the trifield polynomial from that information. But the point here that I want to make is, okay, so from that information we should somehow be able to guess what the train track maps are for these other things. And so basically by guessing, so I don't really have an actual proof that I feel comfortable with, but a heuristic sort of way to guess what the train track maps are for the other ones is you look at the large edges. So the large edges are the only ones that matter. And you look at what happens to them as you do the map. So what will happen is when you're looking at neighboring mapping classes, what ends up happening is that most of the time everything just shifts up. But at some point it's going to have to do that mapping, original mapping class. So you look at, so what happens to this? Well, it wrapped once around, so it goes sort of to the beginning. It wrapped once around here, the first one, and once around the second one. But if you look, but it went over that loop when it did that, so it's going to go something like this. And the other, the blue, what used to be the blue loop, will go something like this. So then and then after that, it's just everything's going to shift up again. And then you remember that these things are connected by these short loops. And let's see. So you can say, well, this point, let's say this is one. This is going to go to 3, 4, 5, 6. This goes to, I should do this on the top like this. Oh, right, sorry. This one goes to here, 1, 2, 3, 4. 4 goes down to here, 5, 6, 7, 8, 9. And then this goes to here. Okay, so you get a numbering. And so this is how I actually found this map. But then I, of course, checked that the dilatation actually is what it should be. And it is. And so here is the train track map for the genus 2 case. And this is a folding decomposition of it. Maybe I shouldn't go so much into detail. You can just sort of see that you get some train track map, and then there's associated diagram over there. Okay, so maybe I'll just show pictures. Okay, so you get the transition matrix, and that is the characteristic polynomial. Now, if you follow this kind of reasoning, then you'll get these train track maps. They'll sort of be repeats of the old one.
This one N is genus N with one.
This is genus 2n. If n is divisible by 3, it
Oh,
goes
is
down.
this one N? One N is the H2.
The coordinates.
Yeah.
Yes, exactly. Right. And also the reason why you can see why 3 is important, because if you look at the number of boundary components, the other than I mean, there's a definite pattern to this thing, and you can see that 3 is important. Okay. Okay, so that gives us a directed graph in general for the mapping classes. And I mean, you have to believe me because I'm thinking over this. But now let's look at the cycle complex associated to it. So the cycle complex, now we're just doing graph theory. Okay, so if you have a directed graph, then a cycle is just closed loop on the graph. And so for each closed loop, you put a vertex. So here, this is an example. Yeah, actually, I think I did. Yeah, here. So there's a closed loop. There are 2 closed loops on the bottom, which correspond to these vertices. There's one closed loop at the top. And then there's one closed loop which goes to A, D, and B, and back up to A. Okay, and then you put numbers based on how long they are, how many edges they go through. Okay, so look at the characteristic polynomial. It's x to the 4th. So it's going to be x to the 4th minus, for every vertex, you're going to put x to that power. So x cubed twice, so 2x cubed, but minus because it's going to be alternating sign. So minus x cubed, minus 2x cubed, minus x squared, minus x. But then for every pair, you put you take the sum and now you do positive because it's 2, so it's going to be x to the 4th and x cubed. So that 2 and x cubed cancel, and you get that polynomial. So without even using the type of polynomial, we can, if we know the train track map, if you know the digraphs, not even the train track maps to the digraphs, then we can compute the characteristic polynomial. So this is sort of think of it as an alternate way of computing the type of the polynomial. So in this case, we know that we get a string of vertices, and n minus 2 vertices along these edges. It's like the original one, just a little bit different from the original one. They just get a string of vertices instead of just the one edge, depending on n. So our cycle complex looks like this, and so the characteristic polynomial is this thing, which is the Leno-Tico set of polynomials. Okay, so I don't have any time, I guess. Sorry, so this is kind of a neat part, but I'll just show you the pictures. This is another way of making a periodic mapping class, and it's just think of it as you're rotating the barrel. But now I flatten it out, it looks like this. And then if you remember what Murasugi, if you know what Murasugi sum is, you just take two surfaces with polygons on them, you glue them together, more or less. So, so here's an example of a hexagon on a surface. And there's the genus 2 example, if you remember from the train track thing, looked like that. So that more complicated train track is really just a Murasugi sum of the genus 2 case with something, with the barrel. So actually that one end sequence, that's all it is. It's just a barrel connected to the genus 2 example. I think that's it.